My dear students, today we will discuss about electrical properties of solids. So mainly, if we consider electrical properties, we consider the conductivity of materials. Conductivity of solid materials, it depends on the valence electron. That means conductivity for solid material is due to the movement of electrons. But if we consider solution, say electrolytic solution, the conductivity of electrolytic solutions, it is due to the movement of ions. Now here we mainly concentrate on the electrical properties of solid substances and the conductivity of solid substances, mainly metals. So now we consider the electrical properties of solids. So electrical properties of solids, we consider conductivity of solids. We can measure electrical properties in terms of conductivity. So conductivity, it is inverse of resistivity of substance, and conductivity is due to the movement of electrons in case of solid substances. So on the basis of conductivity, we can divide solids into three types. One is conductors, then semiconductors, and number 3, it is insulators. Now for conductors, the conductivity range is from 10 to the power 4 to 10 to the power 7 per ohm per meter. For semiconductor, the conductivity range is from 10 to the power -6 to 10 to the power 4 per ohm per meter. And for insulators, it is very less. It is from 10 to the power -20 to 10 to the power 10 to the power -10 per ohm per meter. So on the basis of conductivity, we can divide the solid substance into 3. Mainly conductors, where conductivity range is from 10 to the power 4 to 10 to the power 7. Semiconductor, it is in between the conductors and insulators. It is 10 to the power 6 to 10 to the power 4. And whereas in case of insulator, it is very less, 10 to the power -20 to 10 to the power -10 per ohm per meter. So how can we explain the conductivity of different substances, different solid substances? So there is one theory which is known as band theory. The band theory mainly depends on molecular orbital theory of metals or solids. That means with the help of molecular orbital theory, we can explain the band theory of the solids, and with the help of band theory, we can explain the conductivity of different solids. So now we consider the band theory of solids, and here we consider the conductivity of different solids. And if we consider the band theory, now let us first we consider the atomic orbitals of two different atoms. Say atomic orbitals of atom A this is the atomic orbital of atom A, and this is atomic orbital of atom B, and this is a simple molecule where there is linear combination of these two atomic orbital and there is formation of molecular orbital. Since we consider in terms of energy, this is energy level diagram. So here, so we have one bonding molecular orbital and another anti-bonding molecular orbital. So this is atomic orbitals, AOs, and this is also AO, molecular orbitals, and this is a bonding and this is a anti-bonding. About bonding and anti-bonding molecular orbital, already you know, it is known to you about bonding molecular orbital and non-bonding anti-bonding molecular orbital, and there is energy gap between this. So if we consider a simple molecule, then these are the molecular orbitals of the molecule. But now here, since we consider metal-metal bond and we have large atoms, large number of atoms of metals, and here we have to consider large number of atomic orbitals. So if we consider large number of atomic orbitals that are present in a line, so these are different atomic orbitals of the metal atoms, then when they combine and form molecular orbital, then we will get different molecular orbital. So these are different molecular orbitals, and that has energy values, and we can consider some continuous molecular orbital. That means a large number of molecular orbitals are here, and these molecular orbitals will form a continuous band. In the same manner, we have antibonding also. So we have large number of antibonding molecular orbitals, and these orbitals also form some continuous bands. So if we consider large number of molecules, that means large number of molecular orbitals of different metals, then we have band. Now, with the help of band theory, we can explain why some substances we call conductors and some are semiconductors and some are insulators. So now here this we consider the energy of different orbitals. So these are some bonding molecular orbitals, and say these are some anti-bonding molecular orbitals. Now we have, in case of band theory, we consider three type of band. The number one band, it is called say valence band. And valence band, it is highest filled or partially filled, highest filled or partially filled bonding orbitals. Partially or filled bonding orbitals are known as valence. That means highest filled or partially filled bonding orbitals form the valence band. And this band, it is called conduction band. And conduction bands are formed by lowest antibonding orbitals, which are unfilled. That means which are not occupied by electrons. So here the conduction bands, it is formed by lowest antibonding orbitals which are not filled, and here valence band, these are highest bonding orbitals which are partially or fully filled. So in between these two energy levels, that means here we consider increasing energy. So here in between these two we consider one band, and this is called band gap, actually band gap, or it is sometimes it is called forbidden band. That means in the band theory we consider three types of band. One is valence band, another is conduction band, and another is forbidden band. In between valence and conduction band we have forbidden band. In some books it is written as band gap also. The meaning of band gap, that means in this area, in this energy values, we have no orbitals. That means in forbidden band we have no orbitals having this much of energy. So in case of conductors, if we have conductors, that means metal, then the valence band, it is partially filled. The orbitals are partially occupied by electrons, and the gap, this band gap, it is very less. Therefore sometimes what happen, now we consider separately for conductor and for insulator and semiconductor separately about the band gaps. Now here we consider the conductors now. So in case of conductors, say in terms of energy, here we consider, say this is your valence band and this is your conduction band. Now since it is partially filled and gap is not very more, it is very less here gap, therefore electron from the valence band, say it is VB valence band, it is conduction band, and this is a forbidden band. So electron can easily jump from the valence band to conduction band, and sometimes in case of some substances there is overlapping between the valence band and conduction band, and electron can easily jump from valence to conduction band. So therefore the conductivity range for the conductors, it is very high. It is 10 to the power 4 to 10 to the power 7 per ohm per meter, due to the band gap. Since band gap it is less and the valence band it is partially filled, therefore electron can easily jump to conduction band. So in case of insulator, what happen if we consider in case of insulator, say this is insulator or insulator. Now the gap between the valence band and the conduction band, it is more, and this is say your conduction band, this is forbidden band, and this is your valence band. So gap it is very large. So, and another thing, it is important point here, in case of insulators, then it is fully filled. It is fully filled and it becomes stable, and there is no movement of electron no transfer of electron from valence band to conduction band. Therefore, in case of insulator, the conductivity it is very less, 10 to the power minus 20 to 10 to the power minus 10 per room per meter. Therefore, that means the main important point is, in case of conductor, valence band it is partially filled. It is partially filled. And in case of insulator, it is fully filled. It is fully filled and gap is large. Here it is partially filled, this A. Partially filled and the gap is less. And now if we consider semiconductor, the case is in between these conductors and insulator. Now if we consider the example of conductors, say silver, gold, then your copper, these metals are good conductors of electricity. The conductivity values for these metals it is very high. On the other hand, the non-metals, for example sulfur, phosphorus, carbon, okay, these are insulators. These are conductors, these are insulators. In this case, the energy gap between the fully filled, that means valence band, and conduction band, it is very high. So we consider this as insulators. Now we consider semiconductors. In case of semiconductors, say we had two types of semiconductors. One is intrinsic and another is extrinsic. So main point about semiconductors, as we increase the temperature, the conductivity of semiconductor it is increases. This is very important point, try to remember. As we increase temperature, the conductivity of semiconductor increases. So here if we apply temperature, that means by increasing temperature, we can increase the conductivity and we will get intrinsic semiconductor. And by applying impurity, we can, by adding impurity, we can prepare this type of semiconductor, that means extrinsic semiconductor. So in case of intrinsic semiconductor, what happens, when we increase the temperature, now the energy gap between the valence band and the conduction band, now this is semiconductor and we have gap here, and gap is not very large, and the valence band, it is valence band, and this is conduction band, and this is orbital band or band gap. So when we increase the temperature, the electron from the valence band, that means the thermal energy of the electrons that are present in the valence band increases, and it can jump from the valence band to the conduction band, but not all. That means for some electron the energy becomes sufficient to overcome this gap and it jumps from valence band to conduction band. As a result, the conductivity of the conductor it is increases. For example, if we consider germanium, silicon, then if we increase the temperature, the conductivity of germanium, silicon it will increase. But this increase in conductivity, it is not very large. That means we can't use this semiconductor for practical use, since conductivity is not very large, conductivity values. But if we apply some impurity in, say, semiconductor like germanium and silicon, then the conductivity, conductivity of the semiconductor increase, and this increase is more, and we can use in practical. We can use this semiconductor in practical use. That means in electrical appliances we can use this. Now we will discuss about extrinsic semiconductor in detail. So here it is extrinsic semiconductor. So extrinsic semiconductor, by applying impurities we can prepare this. So here again we have two types, and these two types depends on the nature of the impurities. That means one is called N type or electron rich, and another is P type, and this one electron deficient. Now electron rich semiconductors, now we will discuss. For example, if we consider, say we have crystal lattice of, say, silicon metal. So silicon, it is present in group 14, and in outer shell we have 4 electrons. These are the 4 electrons of silicon. So now in the crystal lattice we have another silicon, and it will bind with this silicon, and again we have another silicon which is bind with another silicon. That means there are 4 covalent bonds, okay? And here also say we have silicon. And now if we apply, this is a pure silicon crystal, and now we are going to add a new element here, and that element, it is present in, say, group 15. For example, say arsenic, where the number of valence electron, it is 5. So it will combine with 4 silicon with covalent bond. Say here we have silicon. It will combine with 4 silicon and forms 4 covalent bond, and another valence electron, say this is the valence electron of arsenic, and now this electron become extra in the crystal lattice. This is not combined with any silicon here. So this silicon will disturb the crystal now. This electron, the extra electron, will disturb the silicon crystal. So what happens now? This electron can, now the extra electron can bind with another silicon, and the another electron of silicon now becomes, say, extra. That means now there is movement of electron from one side to another side. That means again the electron, it will bind with another silicon. That means there is movement of extra electron here. So now since the crystal is disturbed, now the extra electron, due to this extra electron there is movement of electron, and we know that movement of electron, it is conductivity. Now when this type of impurities are present, now the gap between, if we consider the valence band and the conduction band, now there is formation of new band here due to the electron, the extra electron, and that is why the gap now become less in case of the semiconductor, and electron can easily jump from the valence band to conduction band. As a result, conductivity will increase. So this type of semiconductors, where we have added arsenic, the group 15 elements, as a result of which the number of electron become increases and there is movement of electron here. That means electron, it is negatively charged particle. So therefore the number of electron become more, and this type of semiconductor, it is known as N-type, because now the conductivity of the semiconductor increases because of the movement of electron here, and electrons are negative, therefore these are known as N for negative, N-type semiconductor. On the other hand, if we consider, say again, silicon crystal, we have silicon crystal and there is silicon-silicon bond, and we have normal silicon-silicon bond, and valence electrons are bind with 4 silicon. Now if we add one new element, say one impurity element, boron here, and we know that boron, it is present in group 13 and number of valence electron, it is 3. So these are 3 valence electron. Now here if we have another silicon here, now we have like this. That means this side, it become vacant here. There is no electron, though the boron, it is bind with silicon. That means since there is less number of electron is present here, that means there is presence of, we can consider there is presence of a positive hole here, positive hole. And this positive hole, sometimes what happens, this positive hole, it is occupied by the electron of another silicon, and then the another positive hole will form in the another side of silicon. That means there is movement of positive hole. As a result, there is movement of electron. Actually, there is movement of electron from the original side to the hole, and there is formation of new hole in the another side. That means we can consider there is movement of positive hole. So here this type of semiconductor, it is known as p-type semiconductor. So because of these two types of impurity semiconductor, that means when we add impurity, these two type of extrinsic semiconductor we will get, and here the conductivity will increase, and we can use this N-type and P-type semiconductor in our day-to-day electrical gadget, which we can use as diode, and in transistors. If it is only, say, combination of N and P, then we call it diode. And sometimes it is combination of 3, say NPN, that means N-type semiconductor, P-type semiconductor, N-type semiconductor. Say this is combination of or junction of 3 semiconductor, which are generally used in transistors. In case of transistors, we use this. And another one, say PN-type, PNP-type. So, and in case of solar cell also, we use the semiconductors, and this type of sandwich type semiconductors combination, we can use in some transistors which are used in, say, your it is used to modify the audio or video signal. So these are some applications of semiconductors. So we can use these semiconductors in transistors, in photochemical cell, silicon chips, and in case of solar cell also we use this type of semiconductors. So this is about your conductivity of solids. Mainly here we consider metals and semiconductors, that means metals mean conductors and semiconductors. So at home you write the differences between N-type and P-type with examples. Then try to remember the examples, and mainly here when we add the impurities in a pure semiconductor, then the process is known as doping. So they can ask what is doping, it is important question. So what is N-type and P-type? This is important one. And differences between n-type, p-type. Again, what is band theory? How can we explain the conductivity of conductors with the help of band theory? These are important points. In case of insulator, draw the energy level diagram. For band gap, that means apply band theory. For semiconductor, all are important for exam. So if you have any doubt regarding this part, you can ask me, you can clear it. So this is about your conductors and the conductivity of solid materials. In next class, we will discuss about magnetic properties, and magnetic properties also depends on the electrons. That means mainly the number of unpaired electrons that are present in a valence shell, or unpaired electrons that are present in the molecular orbitals are responsible for magnetic properties also. So in the next class, we will discuss about that. So thank you and have a nice day ahead.